Math 30-1. Welcome to applications of logarithmic and exponential functions. So in this, just as the slide says, we're going to look at all the real world applications where logarithmic and exponential equations are used to solve real world problems. As you go through this, these are just exemplars. What we're really trying to make sure we understand is how can we use these logarithmic and exponential functions in meaningful ways. So it's not just that you can memorize these specific cases, but how can we use the idea of an exponential function to solve other problems? So problems that we maybe don't even exist, but these are just a few contexts to deepen your understanding. Example, as you do these questions, obviously I want you to hopefully follow them, but as you do it, I want you to ask the questions, why and why is and how is this working, and so that you're not just copying it down, but you're really thinking critically, because the reality is these are just a sample of the contexts that are used. There are many, many more in healthcare and so on that are used in the real world. So we want to understand the methodology, not just memorize these particular ones. So for example, everything that's exponential in these examples, if we think back to our exponential functions, we can represent every exponential function like this. Y equals a times b to the x, where b is greater than 0, but b cannot be equal to 1. So what we found out is that this can be growth, right? This can be growth if you have something more than 1. If b is greater than 1, then it's growth. But it could also be decay if b is somewhere between 0 and 1. Right, so there's all kinds of examples. There's when we talked about, for example, the vision in water in Cross Lake, and so for example, you might say, well, the amount of light based on the depth in Cross Lake is 100% at a depth of 0, but then for every meter down, you're only going to have about 20% of the light left, so it would be 0.20 to the exponent d. So that would be an example of decay. But we also said, well, we could have the number of cells with respect to time could start out as one cell times, depending on what the growth rate is, but it could be doubling. And in that case, it would be doubling. Let's say it's doubling every 20 minutes. Well, if it's doubling every 20 minutes, then we would have total time divided by the amount of time it takes to double, so that'd be 20 minutes, where t is in minutes. So there's a lot of examples. The key is to really understand the basic of that, the characteristics of the exponential function, so that you can use it in lots of different ways. All right, so here we go. Let's look at some of the examples, and then when we discuss this next day, please bring your questions and say, well, I don't understand why that one worked, or whatever. Okay, so here's a compound interest, one example in how you could use, and notice that in this case, this is our general exponential formula, a times b, and then this right here is that exponent of x. And for each question, it can work a little differently. So you really have to read the context of the question. How is it growing? Is it growing? Is it decaying? And in terms of how often will it grow, or how many times will it grow, you have to consider the total time divided by the period it takes for 1. Right? So in this case, well, we make up a formula, and how long does it take 7,000 to grow to 10? Well, 10,000 is our final, 7,000 here. Well, how much is it growing? Well, it's growing 10% in a year, but it's compounded every half a year, so it's going to grow by 5%. So that's 1.05, and the time is 2t, because it's t divided by a half. In other words, it takes half a year for it to grow one period, one time, right? So if you put 1 in here, it would have grown, if time is years, if you put 1 here, then obviously it will have had time to grow twice. Or if you think of cell division, it would have divided twice, right? So it's grown 2 two factors, right? So if we solve this for t, we take the log of both sides, we isolate, and we end up with time equals 3.66 years. But the question said, how long will it take for it to grow to 10,000? You need to round that up to 4 because at 3.5 years it wouldn't be enough. So you need to going to go all the way to the next growth period, which would be 4 years. So you round it up to 4, not 3.7, because at 3.7, that's not one of the compounding periods. So you need to round up to the nearest year. In the next example of exponential growth, a biologist estimates that number of E. coli. Okay, so read, underline, and you now try and come up with an equation, right? Think, do, and see what you come up with. Okay, now that you're back, I'm assuming you already tried and underlined the keywords, and you've come up with an equation, again, using that basic idea of exponential, and we have the amount of stuff times the growth factor or decay factor and time divided by the amount of time for doubling. So what have we got? Our base is 2 because they talk about doubling. We started with 1,000. We want it to grow to 19,500, and we were looking for the doubling period. What's the period that it takes? So we need to now solve that like we did in exponential equations. We can't write that as a base of 2, so we use logs, and we end up with P is equal to 21. So it takes approximately 21 minutes for it to double. It has a 21-minute doubling period. Okay. Again, write your reflective notes. If there's part of this that you go, I don't get why that's happening, please, before we go to our formative next day, let's ask. Next example, light intensity. Ooh, this is a good one. This is our Cross Lake example. For every meter below the surface, the intensity is reduced by 5%. Every question you have to read critically to understand, well, what's that really doing? What's my growth factor? At what depth to the nearest hundredth is the light intensity? 40% of that is surface. Okay, again, pause, read, write an equation to represent this exponential situation. Now that you're back, I'm assuming you've, again, pondered our basic equation, and you've said to yourself, well, I want 40% left. And this could be 40, or you could write 0.4. You have 100%, which is 1 here, and your growth factor is actually 0.95. Why? Why is it that? Because you've got 100% minus 5 every meter. You're losing 5 every meter. Now this water must be pretty clear. This is more of a mountain lake. We need to solve that for D. Notice there's just a period of 1 meter, so it makes it a nice exponent. There's no fraction. And therefore D is equal to 17.86 meters when the light intensity would be 40%. All right, again, reflect, write your reflective notes here if there's anything about that that is unclear. Now, decibels is a really practical one. We hear that all the time. If you go to a rock concert, you're running a chainsaw, or if you're working, definitely, I know there's town bylaws that say trucks and so on. There's legislation now to keep our noise pollution down. So this is something that's measured by police officers and so on. So what's the definition? The definition of decibels is this. And we can see that the range of decibels. All right. Now, a more, I think, valuable definition of it is if you solve this for I, and I stands for the intensity of the sound. So this is the way you usually see it in the book, but when you look at this version, you say, well, what does it really mean? Well, if IO is a threshold of humidity, so it's a very audible sound. Can you still hear what I'm saying? So like a whisper, not even a whisper, it's the sound where you think, did I just hear something? So if you compare that to a whisper, how much more intense is a whisper than the threshold of human hearing? Well, a whisper is 20 decibels, so if you plug in 20 here, you get 10 to the 20 over 10, and so if you think about how much more intense is a whisper versus this, 20 decibels results in the intensity of a whisper is equal to a barely audible sound times 10 to the 2. What does that mean? It means that a whisper is 100 times more intense than a barely audible sound. And if you now compare that to, let's say, a lawnmower, well, what's the intensity of the lawnmower? Well, clearly, it's 10 to the 90, which would be 10 to the 9 times I-O. So that's 1 billion times more intense than a whisper, right? 10 to the 9, right? That's a lot. Okay, so that's kind of the understanding part of what decibels is. And a rock concert, very much more a jet engine, so you get the idea. So how can we use this? Well, let's look. For any intensity is defined below. Loudness, okay, that's cool. Again, don't forget the other version that we had, and that probably is going to be more useful. So you can plug in the unknowns into any of this, and I stands for the intensity of the sound given, and loudness in decibels. So if you want to know decibels of a sound, then you calculate decibels this manner. If you want to know how intense a sound is, you use the other formula where intensity of the sound is equal to 10 to the decibels divided by 10 times I-O, right? So if you solve this equation for I, that's what you get. And that is usually a more useful version. Okay, so in this case, how many more times as loud is the band playing than the rock concert? Well, let's compare the two. 106 decibels, how does that intensity of that sound work? So we're solving for the intensity. That's that intense of a sound. How intense is the softer sound, the band playing? Well, if you solve it for intensity, that is an intensity of 10 to the 7.6. When you compare these two, what's the difference? You divide them and you compare the soft sound with the loud sound, and you end up with 10 to the 3. Everything divides out, and it's 10 to the 3, which makes sense because the exponent on the tens is 3 units more, so it is 1,000 times more intense than the rock concert. Okay? Yeah, I want you to ponder that. Is there a quicker way to do this question? Can you see it? Is there a better way? I want us to talk about that next day. Okay, so you look. Is there a better way? Is there an easier way? This is good, and it always works. It's using the formula, but I wonder if there's a quicker way. So with pH, we're talking about the hydrogen ion concentration. So this one always boggles my mind a little bit because it's kind of a reverse scale. If we talk about acidity or alkalinity, the lower the pH number, the higher the acidity. So you kind of have to keep that in mind as they ask questions like this. So how many more times acidic is cola versus milk? So who's the more acidic one? Well, obviously cola is more acidic than milk. So when you use your equation, what is the hydrogen ion concentration of cola? Well, 10 to the minus 2.5. And the hydrogen ion concentration of milk is this. So who's the softer versus milder acidic one? So this one is the more intense one, and this one is the softer one. So therefore, when we divide the two and we compare them, cola versus milk, we'll put the bigger one on top, and when we divide out those two concentrations, we end up with a typo, which is 10 to the 4.1. So 10 to the 4.1, how many times more intense is, how many times more acidic? Well, 10 to the exponent 4.1, we end up with 12,589. 12,589.25 times more acidic. So the cola is much, much, much more acidic than the milk, right? So another example. Again, ask yourself, is there a better way? Is there an easier way? So the formula is great, but is there a quicker way that you could come up with that answer when you think about pH? So we don't have to just do it that way, right? And again, it's not this number, that's the typo. It is this number that we really want. Okay, another application, is Richter scale. So we've had the tsunami. We've had lots of we've had lots of examples. We've had small earthquakes on the California coast. We've had even one in Vancouver recently. So this gives an example of the kind of power each of those things has, right? And what kind of Richter scale that kind of event or causes, right? So here's an example. What's the intensity of a Richter scale where M is the measure? So I want you to have a look at that, and now let's use that. Notice that it's not like decibels. We're not dividing by 10, and ponder and see what kind of effect that has. So if we compare these two earthquakes, the 8.9 and the earthquake of 6.9, how much more intense was each of those? Well, when we compare the two, we end up with 10 to the 2, which means that the Japan earthquake was 100 times more intense. Again, is there an easier way? Is there a faster way? Does it make sense? Okay, so ponder that and let's talk about that tomorrow. Is there a better way? Another one would be, well, what if you wanted to know what the Richter scale reading would be? Sometimes that's what we're looking for. But in this case, we were again comparing an 8.1 to a 6.4. Again, we measure those intensities. And we solve them, and we end up with a 10 to the 1.7. Therefore, 10 to the 1.7 gives us about 50.1 times as great as the 8.1. Sorry, as the 6.4. Okay. So before we dive into this, we'll have a quick discussion next class on does this make sense? And now you can dive into these. That's just a selection of possible questions. There are many other ones that I'd like you to try, but at least if you try these, you'll have an idea of what each of those applications does for you. All right, see you next class.